Hello everyone, welcome back to another video. So, for today, we are going to solve an open channel flow problem. Here's the problem. Water is to be transported in an unfinished concrete rectangular channel with a bottom width of 4 feet at a rate of 51 cubic feet per second. The terrain is such that the channel bottom drops 2 feet per 1,000 feet length. Determine the minimum height of the channel under uniform flow condition. What would your answer be if the bottom drop is just 1 foot per 1,000 feet length? So in the diagram, we have a rectangular channel with the following given details. The channel has a bottom width B of 4 feet. Water flows through the channel at a rate of 51 cubic feet per second. The bottom of the channel drops at a slope of 2 feet per 1,000 feet length. The problem also asks us to consider a scenario where the bottom slope is 1 foot per 1,000 feet length. The diagram shows the channel cross-section with B representing bottom width of the channel, Y representing the flow depth of water. So, we will assume that the flow is steady and uniform, meaning that the flow rate and velocity profile do not change over time or along the channel length. The bottom slope of the channel is constant, which simplifies our calculations. The roughness of the weighted surface is constant, given by the Manning coefficient n is equal to 0.014. This coefficient affects how easily water flows through the channel. A higher n values indicates more roughness, which increases resistance to flow. We need to find the cross-sectional area in the weighted perimeter of the channel. The cross-sectional area is the area of the water flowing through the channel, calculated by multiplying the bottom width by the flow depth. So A is equals to the bottom width times the flow depth. So we know that the B or the bottom width is equals to 4, so area is equals to 4y. This is the area through which the water flows. The wetted perimeter P is the length of the channel bed and the sides in contact with the water, calculated as P is equals to B plus 2y. We know that B is equals to 4, so wetted perimeter P is equals to 4 plus 2y. The wetted perimeter is important because it influences the hydraulic radius, which affect the flow rate. Now let's use Manning equation to find the flow rate through the channel. Manning equation relates the flow rate to the cross-sectional area, hydraulic radius, and the channel slope. Since we know the area in the wetted perimeter, we can use it to solve for the hydraulic radius R. R is equals to area over the wetted perimeter. So R is equals to 4y over 4 plus 2y. Substituting the given values into the Manning equation, we get 51 is equals to 1 over 0.014 times the area, which is 4y, times the hydraulic radius, which is 4y over 4 plus 2y raised to 2/3, times the channel slope, which is 0.002 raised to 1/2. Solving for y, we have y is equals to 2.5 feet. Then, if the channel had a reduced slope of 1 foot per 1,000 feet instead of 0.002, we would adjust S to 0.001. We would then repeat the calculations with this new slope to find the new flow depth. So So 51 equals to 1 over 0.014 times the area 4y times the hydraulic radius 4y over 4 plus 2y raised to 2 thirds times the new slope, which is 0.001 raised to 1 half. Solving for this, we get y is equals to 3.3 feet. These new calculations shows how the slope affect the channel design and required depth. That's all for today. Thanks for watching. Don't forget to like, subscribe, and leave any question or comments below.